Hey everyone, so if you've ever had to design a survey, you know the deal, right? You want the most accurate results you can possibly get, but you're always working with a limited budget and timeline. Well, today, we're going to dive into some really powerful sampling techniques that help you get much more precise estimates, and believe it or not, often for less effort. We're going to start with the basics and then build our way up to some seriously smart strategies.
So here's our roadmap. We're going to kick things off with a method called proportional allocation. It's super intuitive. Then we'll see how to actually measure its precision. After that, we'll look at where it falls short and how we can do better with more advanced stuff like Neiman allocation. And to tie it all together, we'll wrap up with a really cool case study that shows all of these ideas in the real world.
All right, first up, proportional allocation. The best way to think about this is that you're trying to create a sample that's a perfect miniature version of your population. It's often called the fair share approach, and you'll see why in a second. It's a fantastic starting point.
The whole idea here is just, well, it's common sense. Let's say you're surveying a university, and you know that 60% of the students are undergrads and 40% are graduate students. With proportional allocation, you just make sure your sample has that exact same 60-40 split. You're literally building a tiny but perfectly representative model of the population you're studying. Simple as that.
So how do we actually do this with math? Well, it all comes down to this one simple formula. Let's break it down real quick. NH is the number of people we need to sample from one specific group or stratum. To get that, you take your total sample size N, and you just multiply it by that group's slice of the population pie, which is NH divided by N. That's it. This little calculation makes sure every group is represented fairly.
Now here's one of the coolest things about doing it this way. It creates something called a self-weighting sample. You know how sometimes in complex surveys you have to add these statistical weights to your data to make sure everything's balanced? Well, with this method, you don't have to do any of that. Because every single person in the population had the exact same chance of being picked. The data just works, right out of the box. It makes the analysis so much easier.
Okay, let's look at a concrete example. We've got a population of 2,000 people, 1,600 males and 400 females. We want a total sample of 400. Well, our formula tells us to sample 20% from each group. So we take 20% of 1,600, that's 320 males, and 20% of 400, that's 80 females. And notice that last column, the sampling fraction, it's the exact same for both groups, 20%. That's proportional allocation in action.
And this is where that self-weighting magic really pays off. Since every single person had a 1 in 5 shot of being selected, we don't need any fancy footwork to calculate our overall average. The average of our sample is a direct, unbiased estimate of the average for the whole population. Seriously, this is a huge time saver when you get to the analysis phase.
Okay, so we know it's convenient, it's easy, it's fair. But here's the big question. Is it actually any better than just closing your eyes and picking people at random? You know, a simple random sample. Let's dig into the math and see how it stacks up when it comes to precision.
All right, I know, formulas can look a little intense, but stick with me, let's break this down. That first part, 1 minus n over n, you've probably seen that before. It's the finite population correction. The really important part is that sum at the end. What that is telling us, in plain English, is that the overall precision of our estimate is just a weighted average of the variances within each of our groups. In other words, our accuracy depends entirely on how much variation there is inside our strata.
And this right here is the whole point. With proportional allocation, the only thing that hurts our precision is the variation within our groups. But with a simple random sample, we have to deal with the total variation in the population. That includes the variation within the groups and the variation between the groups. By stratifying, we've basically just removed that between-group variation from the error equation, which can make our estimates way more precise.
So what does that mean in the real world? Well, think about estimating the average height of students. Let's say we stratify by gender. If, on average, men are taller than women, so the group means are different, and within each group, people's heights are pretty similar, then stratification is going to be a massive win. We've effectively taken the difference in height between men and women out of the equation, making our overall estimate much sharper.
Okay, so proportional allocation seems pretty great, but it's not perfect. It has one major blind spot, a hidden assumption that can actually make it pretty inefficient in some situations. So let's take a look at what that is.
Let's think about this for a second. Imagine you're trying to estimate the average revenue of businesses in a city. You've got a bunch of small local coffee shops, and then you've got a few massive multinational corporations. The revenue for those coffee shops is probably all in the same ballpark, right? Pretty consistent.
But for the big corporations, it could be all over the map. Proportional allocation would tell you to sample the same percentage of both groups, even though intuitively you know you need to sample more of those highly variable big companies to get a stable estimate. So here's the bottom line. Proportional allocation's greatest strength, its fairness, is also its biggest weakness. It treats every group the same, completely ignoring how much variation is happening inside them. This means we end up wasting our sample on the stable, predictable groups while completely undersampling the volatile, messy groups where we really need more data. So how do we fix this? We need a smarter way to do this, a way to allocate our sample that actually takes these differences in variability into account. And that, my friends, is where optimal allocation comes in.
With optimal allocation, we start thinking like economists. We have a limited budget and we want to get the most bang for our buck. We can frame the problem in two ways. We can either say, okay, I've got this much money, how can I get the most precise estimate possible? Or we can say, I need to hit this level of precision. What's the absolute cheapest way I can get there? It's all about making smart trade-offs to get the best possible results.
Okay, now don't worry, we are not going to get lost in the weeds of the calculus here, but the logic behind it is what's important. We're basically telling the math to find the perfect sample size for each group that gives us the lowest possible variance without going over budget. And the solution it spits out is actually really intuitive. It tells us we should take a bigger sample from groups that are larger, more variable, or cheaper to sample. I mean, that just makes sense, right?
Now let's be realistic. In a lot of surveys, it costs pretty much the same to interview one person as it does another, no matter what group they're in. If we make that simple assumption that the cost is constant, we get a really powerful and famous technique called Neyman allocation. It's named for Jerzy Neyman, an absolute giant in statistics who came up with this in the 1930s, and it is a total game changer.
Look how elegant this formula becomes. We get to drop the cost term completely. Now we're allocating our sample based on the total amount of variation in each group. We find that by multiplying its size, NH, by its standard deviation, SH. So we sample more heavily from the groups that are both big and have a lot of variability, because that's where the most uncertainty is. It's just a really, really smart way to focus our effort where it matters most.
So we've got 3 different ways to sample: simple random sampling, proportional allocation, and Neyman allocation. It's time for the final showdown. Let's put them head-to-head and see who comes out on top.
And here it is. This beautiful inequality is honestly one of the most important takeaways in all of sampling theory. It tells us, crystal clear, that for the exact same total sample size, Neyman allocation will always be at least as precise as proportional. And proportional will almost always be more precise than a simple random sample. It's a hierarchy of smartness. Proportional is smarter than SRS because it gets rid of the between-group variation. And Neyman is smarter than proportional because it also accounts for the variation within the groups. It's a clear ladder of statistical power.
Theory is one thing, but let's see how this all works in the real world. For this, we're heading up to Alaska to look at a classic study where researchers were trying to estimate the size of the Nell China caribou herd. This is just a perfect example of Neyman allocation in action.
This table just brings the whole concept to life. The researchers divided their study area into different strata based on where they thought the caribou would be. Now, just look at stratum E. It's not the biggest area, only 70 units, but the researchers knew the caribou numbers there were really unpredictable, a huge standard deviation of 12,000. So what does Neyman allocation do? It tells them to sample that area heavily, 39 plots, to nail down that uncertainty. Now, compare that to stratum F. It's a way bigger area, 120 units, but the caribou population is pretty stable, a low standard deviation of just 1,000. So they don't need to waste resources there, they only sample 21 plots. It's a perfect example of putting your effort where it has the biggest impact.
So what's the big picture here? These aren't just formulas in a textbook. They are real tools you can use to do better, more efficient research. By thinking strategically about how you build your sample, you can get more accurate results, you can save time, you can save money, and ultimately you can have a bigger impact with your work. So the real question I want to leave you with is this: how can you use these principles to make your own research more powerful?